Okay, we have a lot to cover today, and she mentioned that earlier, so we're really just up to Unit 7, and we're going to move kind of quickly through Unit 7, and it's all focusing on proportional reasoning. These are some just things that go with proportional reasoning. We'll go with those. When you think about multiplicative relationships and multiplying, think about how that's different than the way our third graders learn multiplying. When they learn what multiplication is, they're seeing it how? As what? As a group, repeated additions, they're drawing arrays. And so seeing multiplication in that vantage point is helpful, but if you only view multiplication as arrays and repeated addition, then you're really not going to be ready for the multiplicative relationship piece of proportional reasoning. Also today we'll talk about what kinds of problems and what kind of tasks can we give our kids so that we're encouraging that proportional thought and that proportional reasoning, and then connecting that to algebra later. So, and going back to the number sense wheel that we've looked at a few times, we've almost made our way all the way around the wheel. Notice that language again is right in the middle of the whole wheel. When you think about proportional reasoning with just your 5th graders, with 6th graders, what do you think of? What is proportional reasoning? Do we teach it in 5th grade? We compare values, so we compare quantity, such as what? Like values of fractions?
Decimals.
Okay.
We order numbers.
Okay, so she says we order numbers, we compare decimals, we compare fractions. Do you think that falls in our proportional reasoning piece? If you're talking about the value of something, actually you're still talking about that quantity piece or that magnitude. So it does kind of tie in, and when we think of proportions, we think of fractions, and we think of that, but ask yourself, what is the difference between a fraction and a proportion? Go back to Unit 4 when we were talking about ratios, where we did the money and the trash get balls. So just keep that in the back of your mind as we're going through this. A lot of times when people think of proportions, they're thinking of ratios. And what strategy do you think of when you go back to middle school and high school when you're talking about ratios and setting them, or with fractions that you're multiplying? Do you think cross multiplication comes in there anywhere, or do you think that's something with quantity and magnitude? A lot of people do think of ratios and fractions, and they automatically think of cross multiplying fractions. It's so much more than just cross multiplying, and we'll get into something with cross multiplication a little later. Okay, we're going to start off just like we have with all the others, just defining that concept. By the way, in our curriculum, where in 5th grade Common Core Standards, is there anything that says anything about proportional relationships or ratios? Is it technically in our standards in 5th grade? What'd you say? It's in 6th grade. So it officially starts in 6th grade with our Common Core Standards. Does that mean we're not introducing proportional relationships in kindergarten? Are we building a foundation for proportional? We compare numbers, okay. We compare values of numbers. When I think about relationships of numbers, you are comparing them. What about when students are making number patterns? Are they setting a foundation for some kind of relationship? Triangle, square, square. Triangle, square, square. They're looking at that relationship and saying, every time I have one triangle, I have what? 2 squares. Every time I have a pentagon, I'm going to have 3 rectangles. So you're already kind of building that foundation for proportional reasoning and looking at relationships at an early age. When we're working on geometry, we're setting that relationship. But in 6th grade, that's when it technically comes. And I remember before Common Core came in 4th grade, I remember we would see questions on the EOG that were proportions. Like I remember explicitly teaching proportions and pulling out the pencils. You have 1 pencil, that means you get $5. So you have 2 pencils and we'd act it out. That means you have $10. And so I remember specifically teaching that in 4th grade, but it went away and like we said, it officially starts in 6th at this point.
We do with powers of 10 too. If they don't understand that proportional relationship, it's hard to move on with understanding that, you know, a 1 in the 10th place is 10 times greater, and the 100th place is 10 times greater. The 10th place is 1/10 less, and the 100th place is 1/10 less of that, and the 1000th place, you know, 100 times less than the 10th place.
That's
So,
great thinking.
I mean, they don't understand those proportionate, you know, relationships.
So when you're thinking about powers of 10, you are teaching relationships between those values. Great point. I hadn't even thought of that. All right, so let's look at just defining the relationship, or defining what proportional reasoning is. Okay, this is the official definition. It involves a multiplicative relationship between 2 or more quantities. So if we think about when kids see additive, when they see additive relationships, it's a lot of times that's easy to see with pictures. But when you start thinking multiplicatively, that's a whole different ballgame. So when they begin this, when students are just beginning to develop this concept of relationships between things, they have just a very basic magnitude of that. And so that's why we have kindergartners and 1st graders. They can easily look at something and say, yes, that is larger than that. Even preschool kids, you have a stack of chocolates on this table and a stack of chocolates on this table. They can tell you which is larger, which is smaller, which is less, which is more. So they have that at an early age. And then as they develop, they start to get a little more descriptive with their comparisons. They can say, well, this set is 2 more than this set. So they're not just looking at, they're just not using their visual. They're able to be just a little more descriptive with that. I can say that this set's more, but if you think about this set of 4 is 2 more than this set of 5. So it starts to get just more descriptive, and they're processing several things at one time. And so when you think about that, they eventually start figuring out that, like, if you had 6, they have a set of 6, at some point, the more we help develop this proportional reasoning, they're going to realize, hopefully, that this 6, we have a set of 6 and we have a set of 4, eventually we want them to get that 6 is 1.5 times that 4, right? It's 1.5 times greater than that 4. They don't just get to that. Like, we have to really build that and develop it. And so it does develop, and we have to give them the experiences to eventually get to that point. So that's where we're wanting to lead them. So thinking multiplicatively is a lot deeper. It's a lot more than just a basic comparison. And so that multiplicative thinking about that problem, 6 is 1.5 times greater than that 4. That's the key to developing what proportional understanding is. It's not additive comparisons. It's multiplicative comparisons. Okay, moving right along. Let's see. Let's just read through this silently. We view proportional reasoning as a pivotal concept. On the one hand, it's the capstone of children's elementary school arithmetic. On the other hand, it's the cornerstone of all that is to follow. We were just saying earlier, we used to do it, we used to explicitly teach it in elementary. Now we don't technically officially do it until 6th grade, but it is something we start in kindergarten. And it is, if we think about it being the cornerstone of what is to follow, when you think about proportions, how is that going to help what happens in high school? What are they doing in high school that requires them to think multiplicatively? Think about geometry class. Like if they're studying similar figures, like, and we'll see an example of this. This triangle is similar to this triangle. I know the measurement of this. I know the measurement of this. I don't know the measurement of this, and I know the measurement of this is 20. Is there proportional reasoning involved in that? Exactly. That is proportional reasoning, and we'll look at some examples. They're looking for the relationship of the base of the triangle versus this, and so that feeds into it. When they get into trigonometry, sine and cosine and all of that, that is a continuation of this basic proportional reasoning. All right. Something's not right here. I don't want to give you this. Cover it up. Just 1 second. Okay, so we've got a problem on the board that deals with going to require some proportional reasoning. We've got Sam, and this problem is going to continue to show up for the next hour. Sam, we know, can mow a lawn, and it takes him 2 hours to mow 1 lawn. Okay, so think about that relationship. 1 lawn, 2 hours. The question is, how many lawns can he mow in 8 hours? So you know this information about what it takes to do 1 lawn, and you're trying to figure out how many lawns he can mow in 8 hours. Now, what I want you to think about, and don't talk about it with anybody yet, I want you to think about the proportion or that relationship that exists, and I'm going to have you write down, everybody has just some old faded paper. It looks like it's been in here 30 years. I want you to get 1 piece of this paper, and I want you to write a proportion. Now, this is not to insult anyone's intelligence, but we want to make sure we all are on the same page with what a proportion is. What is a proportion? Or just in general, what is a proportion? If you're writing that down, it's 2 ratios. Remember back in Unit 4 we were talking about it's 2 ratios that are expressed with an equal sign in between them, okay? So it's 2 ratios and you've got your equal sign in the middle. So can you write a proportional relationship that represents this equation? And the question is, how many lawns can he mow in 8 hours? That for you may be a question mark or an X. So write a proportion, and write it large because you're going to hold it up in the air. I'll talk about it yet. Write it really large on your paper so when you hold it up, people in the room can see it. Writing a proportion, which is 2 ratios that are equivalent. They've got an equal sign in between them. don't want answers, just write the proportions.
No.
Is this difficult for some of us, or does it come really easily for some of you?
I had to like go back last year when I moved to sixth grade. I had to go back and like teach myself again.
Thank you for saying that. If you don't teach it, it may be a little confusing. She said she had to go back and teach that or study that so that she could do that in sixth grade. Okay. A proportion is going to look something like this. I have one triangle for every 3 squares. How many triangles for 6 squares? It looks like equivalent fractions. We're not talking about fractions, and that's one of the huge misconceptions with kids. And we learned that back in Unit 4. We always teach a ratio is a fraction. Same thing here, proportion is a fraction. We're talking about relationships. So it's going to look like equivalent fractions. So what you're doing is you're making a proportion to fit this story. Okay?
So a teacher has to be able to
Okay, that's how you decide that. Yeah, that's how it is. That's a representation of how to solve that. The definition of a proportion is 2 ratios with an equal sign in the middle. But yes, that is a strategy and that is a tool, and that's how we teach our kids to solve things. Exactly right. Okay, give your paper to somebody else. Some of you are nervous. I don't really like this. Just switch it around so that you're not holding up your own and nobody's going to judge you based on what you're holding up, because we know it's not really your paper. All right, hold it in the air and turn it so that folks around here can see. I'm going to have a couple of you call out just because the pencil's hard to see. Do you care to read your proportion out loud for everybody?
Gosh, yes.
Oh, it's not your paper though. It's not your paper. Okay, I don't want you to feel uncomfortable. We'll go somewhere else.
I don't care. I really don't.
Okay. So up at the top, it's 1 log equals 2 hours, and then blank logs equal 8 hours. And then it has 1/2 is equal to something over 8.
Okay, so she started, whoever's paper this is, they started writing it out as an equation to help them form that. 1 log equals 2 hours. That's what they do. And then she went on. So your final answer, your final proportion look like what?
1/2 equals something over 8.
1/2 is something over 8. Who else had that on their paper? So what does that 1 represent? Longs. And we constantly have to ask our students, what is the unit here? Otherwise, we think they're talking about purple monkeys. Okay? Who has a paper that looks totally different than this? I know they all wouldn't have that. No. Who had something different? Okay. Oh, yours is different. Yours is different. Okay. Her relationship says 1/something equals 2/8. Okay.
And we use ratio though. That's a ratio.
Oh. No, you wrote it as a ratio.
Yeah.
Sorry.
Yeah.
But your proportion ended up looking different. So they started out as a ratio, just like we do when we do analogies in reading class. I like that. She said 1 is to 2 as blank is to 8. So they started there and then wrote a proportion using that information. Okay, did nobody else have a proportion different? Okay, we're going to have to stretch our brains a little bit. I want you to think of another way to write that proportion. Talk about it with your tables. Is there another way to write it? The answer is yes. Let's just see if we can come this one.
Well, that would be similar.
It
Like,
was a
solve it.
representation.
Yeah.
Solve it. Picture 2 creates the same. So 1, 2.
Was anybody able to come up with anything different? We did have a table that was being Sean didn't share. We really did have another proportion. Okay, you got something different?
Yeah, this one just flip-flopped it and put 2 hours over 1 lawn equals 8 hours over how many lawns?
Does it help to put some kind of label there? I noticed, is it okay to do that? She said we just flip-flopped. What did she flip-flop? The label. Are we going to call it a numerator and a denominator? No, because we're not talking about fractions, we're talking about relationships. Instead of looking at lawns to hours, she said look at hours to lawns. And then over here, hours to lawns. And is that okay? Am I maintaining the same relationship? All right, who has another way? I'll share this one. This group says 2 hours, 1 lawn, 8 hours with blank lawns.
What about using a bar graph? I mean, the bar graph.
She says, what about using a bar graph? And this lady over here says, I'm using a T-chart. Yes, those are ways we can solve them. Right now, we're just setting it up. But yes, we're going to look at multiple ways to solve them. What do you think about this? Am I maintaining some kind of relationship here? Hours, lawn, hours, lawns. Hours, hours, lawns, lawns. Am I maintaining that same relationship? So would it work? It may not go in the order that I've read it if I'm going this way, but I'm writing it this way in the order I read it. Okay, are there any others?
I said you could do it on a line graph where you plot 1 and 2 and then draw a line through that up and it would line up as you went 2 to 4 to 8 to...
Perfect. Are you sure you guys haven't done this before? Are you sure you haven't done this? That's exactly where we're going to be headed with this. You're exactly right. All right, any others? Okay, so everybody hold up your proportions in the air. I'm going to do a little geometry here. Put your hand on each side, and I want you to rotate it clockwise 90 degrees. Okay, rotate it clockwise 90 degrees. Now pretend that it's not sideways. Pretend that it doesn't look funny, okay? When I take this one and I rotate it 90 degrees, I now have, when I take this one and I rotate it 90 degrees, it looks like this. Everybody see that? Do this. Oh wait, I rotated the wrong way. I rotated counterclockwise. Darn it. Okay, write down your new proportion with what it looks like now. Just pretend that your digits are formed correctly. And you have room in your participants manual on page 2 of Unit 7 if you want to jot that one down. So what I should have done is I should have okay. My proportion looks totally different now. Okay. You've written that one down. Now hold it back up. and rotate it 90 degrees clockwise again. And then write that proportion down. This looks very different than your initial proportion, doesn't it? Now the question is, does it match the story that we're talking about? The one that you just wrote, does it show a relationship between the lawns and the hours? And are you maintaining that relationship? In other words, is this a correct answer also? Is this a correct answer? Is this a correct answer? Is this a correct answer? Why? Why are all of these the correct answers? What? Oh, everybody say that. It maintains the relationship. I'm not flip-flopping, and I'm so glad she used the word flip. I'm not flip-flopping other ways. I'm not flip-flopping diagonally, or when I do rotate it, that relationship maintains the same. Hours to hours, lawn to lawn. Lawn to hours, lawn to hours. Okay? So in thinking about that, can you think of any others that are not on the board? Look up here and call out any others that I don't have written. It could be, I could take this and just move it over. 1 over something equals 2 over 8. Does anybody have any others that are not on the board? Again, all of these work because I'm maintaining that relationship. Now we need to think out of the box just a little bit. Can you write down in your participants manual an example of a proportion or a non-example of a proportion for this? What's something we might see our students do? What is a non-example? Something that would not match this story. In other words, something that's not maintaining that relationship. Yes, using this same story with the same numbers. What is a non-example? What's a wrong answer, in other words?
1 over 8.
Huh?
1 over 8, 2 over question mark.
Okay? She says 1 over 8. Let's look at that. What does that 1 represent?
The 1 long.
Long. And the 8 represents the
Hours.
Okay, and that is equal to what?
2 over question mark.
2 over question mark. What does that 2 represent?
2 hours.
So hours.
2 hours.
And the question mark represents the long. She says this is a non-example. Do you agree or disagree? This is a non-example because we're looking at the relationship between lawns and hours, and then we come over here and look at the relationship between hours and lawns. You can't do that. You're messing that up.
If you put 2 on the bottom, that still would be wrong, right?
If you put 2,
Yes,
Because the 1 and the 8.
Not 1 hour, it's not 1 long 8 hours.
okay.
No, that's not true. We did
Could-
that before.
If I do this, am I messing up? Oh, sorry. If I do this, am I messing up the relationship? Lawn hours.
Because that would be lawn.
2 hours to mow 1 lawn.
Yeah.
The number of
It's okay. Can I look at the relationship going this way? Lawn, lawn, hours, hours. Can I do it that way? what numbers would match here?
You can, but
The numbers are wrong.
but one doesn't go with 8.
How many lawns
In 2 hours.
in 2 hours? You're saying we can't do that because one doesn't go with 8?
That's right. 10 hours.
One goes with 2, so our relationships are all messed up, aren't they? Okay, so we have to maintain that. So we can look at the relationship going this way, or we can look at the relationship going this way, but we can't start mixing them up. Good job. All right. Any questions about that piece? Okay, so what we have here is we have our original story, and instead of using numbers, we're taking it back to the concrete. Because a lot of times when we begin looking at proportions, we go straight to the numeric values of it, and we go straight to what looks like a fraction, even though we're not talking about fractions today. A fraction is an actual value on a number line. We're not talking about number lines. We're talking about relationships between two what? Between two quantities. We're not talking about a quantity. We're talking about the relationship between two quantities. So this looks like a fraction. It is not a fraction. So we've just taken it back to the concrete level here. So the lawnmower represents what? The one lawn that I mowed. The 2 clocks represent what?
2 hours.
All right, so the 2 hours. So we're just showing this relationship at a concrete or a visual level, okay? All right, so here we have it. 1 lawn, 2 hours. If I mow 2 lawns, how many hours would it take? 4. How many lawns would I mow if I mow for 6 hours? 3. And I've solved that by using this visual representation. And we have some ladies over here talk about other great strategies. So we can't forget and we can't overlook, we can't skip this step right here. That way our students are looking at these numbers and tying them to some kind of quantity. All right, here's another, and we had a lady at this table looking at this. We're going to take this same proportion and we're going to show it in a different way with our teach right here. So what we did here is we took that our first story, and we extended it, okay? So that's real important to know later. We had our first story, and we extended it, okay? So we could fill out a chart like this. Our students, do you think you'd have 5th graders that would solve it this way? Yeah, so I have, if I mow 1 lawn, how many hours does it take me? 2. So what I'm doing here is I'm showing my 2 quantities. I'm displaying 2 quantities in a different way, okay? So on the next one, if I have 2 lawns, how many hours did it take me? 4. So I've taken this original story and I've extended it, right? Okay. If I extend this story again, what's it going to look like?
3 to 6.
3 lawns
6 hours.
with 6 hours. I'm extending the original story. So I'm looking from here down to here, okay? If I extend it again, what is it going to look like?
4 to 8.
4 to 8. Okay. All right, so we do have students that need this. And we want to expose it in this form. All right, another format that we could express our proportions, because what we're doing is showing the relationship between 2 quantities. Study that for a second. All right, so talk to the people at your table. How does this show a relationship between 2 quantities?
Right.
Do you? Don't you just grade? Alright, somebody share out what your table said. How can a double number line show a relationship between two quantities?
As long as you're maintaining the relationship on each line, you're fine. So like, if you're counting by one, you're going to count by one on the long number line. If you're counting by two on the time line, you're going to count by two. As long as they line up to each other.
Okay, she pulled out some very important things. She said, as long as you're maintaining a relationship, and then she said counting by ones, counting by twos, as long as they, what'd you say?
They are lined up.
As long,
You would do the 1 hour with the two, or 1 long with 2 hours.
good. She said as long as they're lined up. So I can use a double number line to see if I mow 4 lawns, how many hours is it going to take me to do that? 4. Is this any different than this? Is it any different than? Oh, I took it out. Than what we had on the board. No, it's the same thing. It's a different way to show it. If we only expose our kids to the digits, to the numbers on the board here, they're not able to make connections to real quantities. Even 5th graders need that. They need to be able to make that. And I was real excited back here when I heard this group talking because, will you remind me of your name? Janine made a connection. She made a connection between this version and this version. What was your connection?
When you look at the number lines, you immediately see 1, 2, 3, 4, 5, 6, 7, 8, 2 together. So it's the same thing up here. 1 long, 2 hours, 2, 4, 6.
We want our students to see the connection between this quantity and this quantity. We want them to see the relationship between this quantity and connect it to this quantity. So making that connection. And if we zoom through it and don't give them the chance to connect those pieces, we may find some gaps. All right, look, in thinking about number lines, what if we took one of those lines and rotated it? We could have a coordinate grid, which is what someone mentioned earlier. So this x-axis represents what? How many lawns? It's an actual quantity. It's how many lawns you've mowed. The y-axis represents the hours, how many hours it actually took. Now we're talking about proportions and relationships. How can this show a relationship between the two? Yeah, I can plot points on there, but where's the relationship piece of that?
Connect your dots and pictures of lines.
Oh, she says maybe when you connect your dots, you'll be able to see some kind of relationship. What kind of relationship are we going to find?
You might want to add a row of lines.
Okay, she says we're going to make 2 lines. Would we make 2 lines on this?
Or just one.
Do 1 line.
How many quantities are we talking about? 2. The x-axis represents one of those quantities. The y-axis represents the other quantity. So if we plot it on a point, that point represents that relationship at that time. So if we did that, what would another line, are there 2 relationships existing here or just one?
One.
So how many lines will we have?
1.
Okay, so what will this look like? 1 lawn, 0 lawns means how many hours? 1 lawn means 2 hours. 2 lawns goes with 3 lawns and 4 lawns. Now someone said if we connect those dots, we have what kind of relationship? A linear relationship. How is this going to help them in high school? Very much so, right? But again, we're just using a coordinate grid to show the relationship between 2 quantities. When we were writing the numbers on the board here, some of us were looking at relationships this way. Looks like a fraction, but it's not. Some of us were looking at relationships this way. So there are actually 2 different multiplicative relationships that exist within proportions. And this is one of the types of relationships, and it's called scalar. And this is the relationship that kids mostly get first, okay? So the example we just did with the sand mowing the lawns has a scalar relationship because we're looking at values from two different measure spaces. In other words, we're taking that story and we're extending it. We started out with one story and we found the relationship when we extended that story, okay? So we're looking at a multiplicative relationship and we're moving between different scales. We're looking at we're looking at the relationship with that story being extended into a different story, okay? So that's called a scalar relationship. All right, here's what it's going to look like on here. If we look over on the lawns side and look at the relationship between the first picture and the second picture below it, what's the multiplicative relationship there? Times 2. Look over at the hour side. From the initial story to the extended story, what's the multiplicative relationship? Times 2. Now go back up to your original story and look at the picture. What would the relationship be between the original story and this story? Times 3. Is it going to be the same thing over here? Yes, it is. And then what's the relationship between the initial story and this one? Times 4. Okay? So that's happening on both sides. So I'm looking at the relationship from lawns to lawns, from lawns to lawns, from hours to hours, from hours to hours. Sometimes I get confused between the difference of scalar and the other type, and this is what, in my mind, helps me picture that. Okay, so let's look at the double number line. Where does the relationship fall here? If you start at your original story and you extend it, what's the relationship going to be on the lawns? Times 2. What's the relationship on the hours? Times 2. It's that multiplicative relationship. Now we're going to extend the story and kind of look at a different one. What's the relationship going to be here? Times 3. Same thing with the hours. And then what's my multiplicative relationship over here? Notice I'm not looking at the relationship from here to here. That's a different type of multiplicative relationship. We're looking from lawns to lawns, from hours to hours. Any questions about that? Okay, what's it going to look like on our coordinate grid? What's the relationship from our initial story to the extended story? What happens to my x-axis? How's my relationship going to look here? I lost it for a second.
The second dot would be times 2, the third dot would be times 3, and the fourth dot would be times 4.
So the x value is going to be times 2, times 3, times 4. You see that? What's going to happen with my y value? Times 2. Then I go back to my original, times 3. Go back to my original, times 4. You're exactly right. So you're always going back to that original story to find that relationship. That's what makes it, what kind of proportion? Scalar. Scalar. Okay. The second type of proportion is called a functional proportion, and that's where you're looking for the relationship within the same measure space. And we're going to find that in these that we're maintaining that proportionality or similarity. And in my mind, this is how I think, but the research says that the students see it, the scalar, they I guess, inherit that first. But let's look and see what the functional looks like. The functional relationship is not going to go from the original down. It's going to go from the number of lawns to the number of hours. What's the relationship there? Times 2. What's the next relationship going to be? 2 lawns, 4 hours. Times 2. What's the next relationship going to be? Times 2. And the next one? Times 2. So we have a unit rate. We maintain that proportionality. But what's the difference here? We're comparing lawns to hours. And in my little mind, that's just how I think. To me, that just makes more sense. I've come up with my unit rate. Every lawn means 2 hours, so 2 lawns would be 4 hours. And that's just how I think. So it's really hard for me to back up and think in that other direction. So we have maintained the same relationship. Whereas in the scalar, the relationship was different every time. Okay? All right, what's it going to look like with our double number line? How can we show the relationship there? Or where is the relationship? You're comparing the quantity on the top to the quantity on the bottom. So what is that relationship? Times 2. All the way across, right? Times 2, times 2, times 2. That's a functional relationship. I'm comparing lawns to hours. And it's the same relationship throughout. Okay? How does this show relationships? Where's it going to show on a coordinate grid? Where are we maintaining that times 2, times 2, times 2? Talk about it.
It's 1 x is 2 y. Where x is 1, y is 2.
She says where x is 1, y is 2. Is it like that every time? Are we going back to the original story, or are we just looking at it from one dot to the next? Okay, when we start with nothing, we're going up 2 and over 1. If we do it again, from that point, we're going up 2 over 1. Up 2 over 1, up 2 over 1. So our y, what remains constant there? The 2. That's our functional relationship. So that's how it looks different there. Don't you think you have students, some students that are really going to connect with this version? Or I think a lot of students are going to connect with this version, right? Some students may connect with this. Some students may connect with this. But our job, if any of you go to middle school or if you have 5th graders that you're really trying to accelerate, our job is to give them experiences with all of these. Okay?
My problem with my kids, my 6th graders, is that they have trouble going back and forth. We're working with the same problem, and I'm asking them to go back and forth. And they want to look at the functional, not the scale. They don't like going back and forth. That's hard. It's hard for them to switch their brain like that.
And that's exactly what I stood up here and admitted. I think in a functional relationship manner, and it's hard for me to move over to that scalar side. And when I'm forced to do it over, I may tend to prefer one kind, but I also have to be able to understand that, because think back when we did ratios. We had the money problem and the basketball problem. You have to be able to understand when it's a ratio and when it's a fraction. And in some situations, there may only be a functional relationship and not a scalar relationship. Or is there always both?
Well, it's probably just kids like it clear cut. They don't like to deal with decimals and fractions, and so one of the the scalar relationship might be a whole number, but the functional relationship might not be. Like that.
Okay, that's brought up something I forgot to mention. How can a double number line help us with rational numbers later on? They can see equivalent fractions, even though we're not doing fractions here, they can see equivalent fractions through something like this, right? So if I say I mow 1.5 lawns, well, I could do it with a proportion. 1.5 lawns, how many hours is it going to take me?
2, 3.
1.5 lawns. 3. It's going to be right in the middle. That relationship is going to line up. So it's going to take me 3 hours. If I work for 7 hours, how many lawns will I mow? 7 hours, 3.5 lawns. So you can start and you can go in deeper that way. Thanks for mentioning fractions, because I think that's.
Misty, can I say something real quick? I love at the beginning of this how you had us create our own ratio.
and that's what we do with our students. Solve it however you want to. And I think we just learn about ourselves, what we prefer, functional or scalar, based on what we put as our original thing that you wrote up there, the relationship, the ratio. Because some of us did functional, some did scalar, even though we didn't show it in a drawing. But the way we were processing that was definitely.
You tend to stick with that one relationship. So when it looked like a fraction, you tended to either stick with your relationship looking at it vertically, or you did it looking at it horizontally. So that tied in to the scalar functional. Good, thank you for pointing that. Okay. So what I want you to do for just a second, you can do this with your group on a sheet of paper that's in the middle of your table. I want your team to draw a Venn diagram. On the left side, write scalar. On the right side, write functional. We all know how a Venn diagram works. What happens in the middle is something that they both share. Okay. Yeah, just one Venn diagram. Will you take just a minute and try to find at least 2 differences and 1 similarity? So complete a Venn diagram based on what we just did there. What's different about scalar and functional, and then what do they both have? You have a great slide in your participant manual, by the way, if you need to refer back to it.
They both compare, scalar compares like units, and functional compares like yes. I would have to be careful.
They are then we do. Yes.
So when they
But we're in the form of so that's just doing the number line is a good between the corrections.
This like she said, this should be where this one is not relationship, this is just relationship. And I think that's true for everybody. That's why we talk about rationality.
you're forced to look at this.
At least there's one and then
Okay, let's come together and see what you came up with. Is anybody willing to share one thing? What's something you put on the scalar side that represents a difference between scalar and functional? Any volunteers? Thank you, ma'am.
Scalar has different measured space where functional has the same measured space.
Okay, scalar has a different measure space, whereas the functional has the same measure space. And what does she mean by measure space? A different measure space. We're going back to that original story every time, and then we look at a different measure space. We go back to that original story and look at a different measure space. Whereas with the functional, we had that same measure space throughout. Very good. All right, who has something different? You want to talk? It's in the interview. Oh, it looked like you were getting ready to say something. So,
Different situations.
different situations for the scalar and the functional.
It's the same situation.
Okay. Again, it's because you're going back to that original story. Thank you. What else? Did anybody put anything about the relationship? With that scalar, the relationship is different, right? Our relationship was, that's right. The functional relationship is constant. It was always times 2 times 2 times 2 times 2. So with the scalar, the relationship is different. With the functional, it's the same. Any other differences you want to point out? What you put in the middle of the two? Multiplication, multiplicative relationship. We had a teacher up here said, I purposefully use the word multiplicative with my students all the time, and it blows their minds. Good for her for doing that. They're going to hear that, and they're going to develop that. Okay? All right. When we look up here at our pictures, we've got we're comparing longs to longs with the scalar. With the functional, or we can do hours to hours. And with the functional, we're doing the opposite. And that's what you just said. Longs to hours. All right. How did you do with your Venn diagram? Pretty good. All that. That unit rate is what we meant when we said the relationship stays the same. That scale factor means the relationship was different with each one. All right, we have somebody that pointed out something awesome that I never thought of, and I loved it. You know how we talked about with that double number line, if you take one of those numbers and you make it vertical, you form your coordinate plane? Think about what could happen if you take one of these and you make it perpendicular like this. Then you can go and build your T-chart, right? But the difference is
You go from scalar to functional.
it goes from, if you're looking at it this way, you're looking at it scalar. If you're looking at it this way, you're looking at it functional, right? I never thought of that. We can take the same information, and on here we can look at it, the scalar relationship. We can flip-flop and look at it this way, and it becomes a functional relationship. All right, third graders, what are they used to seeing in the format of this? Other than a T-chart. Somebody mentioned earlier, input-output tables. They're familiar with that, aren't they? They're used to that. When they're doing those input-output tables, are they expected to find scalar relationships sometimes?
Yes.
Are they expected to find functional relationships sometimes?
Yes.
Yes. And we try to expose them to both kinds, don't we? We don't want them just to go with one. All right.
A lot of times they'll leave out one of the numbers too. You have to figure out which one, and that's a good way to do that. They were having practice with this, setting this up. Then you take away the 4 hours or the 4 months, they can figure out what goes where too.
They can without the
And that's a good way to practice that problem solving.
Okay, now I'm going to have you try. We're looking at similar pictures here, so maybe we moved up a little bit to high school. Got this beautiful picture, and the dimensions are 5 inches by 10 inches. The larger picture is a 15-inch by something. Okay. What I want you to do, and I don't mind if you do it with your table or you do it by yourself, we're going to solve this 2 different ways, okay? I want you to solve it one way with the functional relationship, and then solve it another way using the scalar relationship. And let's see how it looks different. Think about scalar and functional. You have room to work on page 6 in your participants manual. So what we're pushing, we're solving it, we're doing escape.
Where I would see,
What do y'all think?
it depends on which one we use.
Okay, so if you're using skate, if I'm using, so if you're using skate, what you're comparing light, so you need to go width to width, length to length, so what would that look like?
10 question mark. But if we're doing
So I would do that one as a fraction.
Yes, because you're comparing different length to width, unlike equals, yes.
You're saying if you didn't have that big and small, then you wouldn't have to.
One is length to length. 5 has 10.
Oh, on the same.
Sorry, Mitz, you get a lot of airtime today. Sorry.
I like the way you use the double number line.
You're right in the little shot.
Because of the way they're made, they're so the shot when I put it to the sun, and sometimes the shirt doesn't fit quite well, so I'm wondering if I should put it in frizzy, but I don't want it to be too big.
Alright, how many of us got a little more confused with that? How many of us did it kind of come together? Okay. We were functional and the scalar to determine the length. So if we solve it using the functional relationship, what's our answer going to be?
Say that again, would you ask that?
What is our answer going to be to this question mark here? 30. That's if you solve it with the function. If you solve it with the scalar, what's our answer going to be? 30. So we're not getting a different answer. It's just two different approaches, right? So if we're looking, this everybody's mind thinks differently, but this is how I remember the difference. When I think of a T-chart and I think of my labels, if I'm comparing this way from width to width or from length to length, then that is a scalar relationship because I'm comparing like units. If I'm going this way and I'm finding the relationship between two unlike units, then which proportion? Then I'm using a functional. And I remember that by function table. When I have a function table, I go over this way, so that's kind of the way it's for me. So if you're solving this with this functional relationship, what is the unit rate? What is that constant relationship? Multiply by 2. Because 5 times 2 is 10. So 15 times 2 is going to be my 30. That's my unit rate. Okay, if I'm solving it with a scalar relationship, I go from width to width, length to length, right? So for this one, what's my relationship? Times 3. And that stays the same, so times 3. So 30 is the answer, and you can look at it either way. But it is important that we expose our kids to both types of relationships because different stories are going to lead them or lend them to one particular type. Okay, let's look at the diagnosis here with proportional reasoning and what that means for us. When we are looking at proportional reasoning, we know that it's foundational to that higher math. When they're looking at similar figures, when they get into trigonometry, and students it doesn't always go hand in hand with symbolic representation. Notice we talked about cross multiplication earlier. Does cross multiplication have anything to do with what we've just been doing? Are we multiplying things? A lot of times people think of cross multiplication when they think of this, but cross multiplication in this particular sense doesn't mean anything, right? We don't do that. We have a sense-making strategy, not some memorized algorithm, okay, that we've gone to. Reasoning does not always go with that cross multiplication. And I wanted to reiterate the fact here that we can't tell our kids it's just a fraction. It's totally different. We're talking about relationships. We're not talking about a quantity. And students get so easily confused. Well, is it a fraction or are we talking about a ratio? Is it a proportion or a fraction? Because they think it's the same thing. It goes hand in hand, and it's not. It's not the same thing. Okay, when we're looking at proportional reasoning, research has showed that there's 4 different levels of strategies that students use. And one of the first strategies is just an additive strategy. And that's not going to get us anywhere because proportions doesn't have anything to do with adding, does it? It's about what kind of relationship. Multiplicative. Sometimes when they have a T-chart, they'll look at that and they'll add and say, oh, I added and I got that answer. I basically got there by luck, so it's going to work every time. That's where a lot of our kids are. The level 1, I said level 1, that's level 0. Level 1 strategy is where they're actually using manipulatives and things to find that relationship. You have some pattern blocks on your desk, and you have some square tiles on your desk. Will you build some kind of relationship will you make some kind of relationship using the materials on your desk? So it could be a pattern. Like I thought, I'm going to do 3 hexagons for 2 squares. Then I'm going to do 3. If I have 6 hexagons, I'm going to have 4 squares. Can you build some kind of proportion with concrete materials? you showing scalar or are you showing functional?
I'm sorry, that song was on the radio this morning.
Oh, you were using it. Oh.
Which is what you did.
Which is what we did on that double number line. She has to see the relationship every time, and she does it with different colors. So we call it the rainbow.
You were saying this is the one that I'm telling. This is the way I used it. And I haven't that much of this. I talked about it a little bit, but not. She's the later.
You know why I think that I've learned that because I was never taught. I was taught back in 1980 where you start with the digits, images. I think that's why it's ingrained in me. I don't think. And it came back to what they needed was the need was ownership, shared as a whole. That's what we're talking about. Money, common sense. Okay, somebody share out what proportion were you able to build at your table? This cute little group made an equal sign with paper clips. Look at them. Does anybody want to share out?
3 triangles equals a trapezoid.
She says 3 triangles equals what?
A trapezoid.
A trapezoid. So for every 3 triangles, I have 1 trapezoid. So can she extend that?
Yes, I just didn't have enough.
So she extended it. So 6 triangles means 2 trapezoids. 9 triangles is 3 trapezoids. Is that scalar or functional?
Scalar.
If you look at it,
If you look at it this way, but if you look at it this way, it would be scalar. So this is functional.
Depends on how you're
This
looking
is
at
the
it.
scalar
If
part.
you're going back to that original story and finding that relationship, it's scalar. If you're looking at it this way, it's functional. Okay, I tried to trick you with that question. Okay, so this is level 1 of the strategies the students use. Level 2 is when they begin to see the relationship there with multiplication division. That's when they actually see that divided by 5 is the same thing as times 1/5. Remember we were talking about our bean party and did we? Yeah, we did the bean party. Multiplying by the reciprocal. That's when they begin to see that relationship. Level 3 is when students start cross multiplying, and a lot of times we go straight to strategies like that. That's our entry level most of the time, isn't it? And we've totally missed the boat by doing all of these other things. So. All right, so here are some student issues that we see. I don't think there's anything. Students don't analyze the relationships among the symbols. And they use a cross product method even when they're within or between the relationships. Let's talk about student issues for just a second. We're going to do something called speed dating, then we'll take a quick break, okay? Everybody will stand up. two lines just coming down the middle aisle here, just facing each other. Something told me you needed to move a little bit. Come stand and face someone.
I'm sorry, I can't speak date, I'm in a committed relationship, I'm married, sorry.
Come face somebody. Thinking about
I don't wanna be
all
on
issues
camera, Jill.
of
I will break
proportional
it.
Only
reasoning.
people from DPI see it.
What you're gonna do is you're gonna talk for just a second. This looks just like you see on TV, where they're speed dating, and then you slide down and you talk to somebody else. Then you speed date and then you talk to somebody else. This is a great way to, in your classrooms, you can check for students' understanding. What I want you to do is just talk for a second with the person around you, 30 seconds, about what are some issues you can see with proportional reasoning, about why it's important for us to resolve certain student issues before going straight to algorithms. Just talk about some issues you might see or some roadblocks you have with students in your grade level. Just issues, roadblocks, concerns, anything about what we've done so far, okay? Go.
What it's asking you to do, problem strategies, and then they're interpreting that in concepts bringing you some information, it's not all, they see it all actually involved. So let's just, when in doubt, let's just go right.
Just stop. Thank you. If you're on the road closest to me, you're going to slide to the right, which means you're going to come all the way to the end here. Hey, if you're on this road closest to me, everybody slide to the right one step. You have two partners. They're speed dating. Okay, 20 seconds. Share some issues, concerns, aha moments, anything from proportional reasoning so far. Go. One more time, but this time when you slide, I want you to share something that a previous partner has shared with you, okay? So this is not your thoughts, but maybe something that someone else has just shared with you. So if this row will slide one more time, and if you're at the end, come back this way. Ready, go. Share something that someone shared.
Very difficult, and they all struggle with that. One concept, knowing what this concept is. So this is going to operation. You do it by itself. When in doubt, either that everything is
Thank you. You all did a great job with that. Can you think of a way in your classroom that you could use this strategy to help them communicate and get that mathematical discourse going? You could even call on a student and say, share with us what your partner said. That way it takes the heat off of them. But, and I don't know that I call it speed dating in elementary school. What could we call it?
Well, isn't there,
Skip.
Do it in a
Parallel up.
The parallel circle. Parallel shifting. Yeah, then we're getting that terminology. All right, guys. We're going to take a short break. I know you're dying to use the bathroom and get some water stretch. So let's come back together. What do you think, Jill? 10 minutes?
Yeah.
10 minutes. So at 9:55.